So now I wanted to look at the other topic in this chapter, which was on momentum, right here, rotational momentum. Remember, we defined the rotational force as R cross our old force right here. Well, we're going to define our rotational momentum as R cross our old momentum right here. So we always just make it R cross. The reason why we want to put that cross product in there is because if we want to just find the momentum of this right here, you notice this momentum, this little particle is going that way with mv. This one over here is going this way with mv. If I were to add them up, I would get 0. But if I add up their r cross mv's, r cross mv is in. Over here, r cross mv is also in, and that way they add to each other. They don't cancel their effects out. Remember, linear momentum, remember P was mv, and then we said if the total forces, which is they always are when you include the whole system, if that's 0, then momentum was a constant right here. That's why we could look at it for collisions. We looked at the entire system. But now we can say if the torque on the system is 0, the total torque, then the angular momentum is constant right here. That is, this for all the objects is constant when you add them all up. Well, let's say we have an object like this, just a disk spinning right here. Well, then we just add up all the little r cross p's of all the little pieces going around. Well, the angle between all the r's and all the v's are 90 degrees. So I can get rid of the sign of the angle between them, and it's just r times p. I can turn my p into mv, and I can turn my v into r omega. And this was just my I, and that's omega. So this, remember, our regular equation was p equals mv. Now, since we're just switching letters, we switch the p to L. That's angular momentum. We switch the m to I, and we switch the v with omega right here. So the equations are still the same right here. Okay, and we have to take this thing about an axle right here. And just like with torques, it's about a point. Now, if the object's not rotating in a circle, then you're going to have to come back to the general definition right here. This is only true if it's just like a spinning object right here, but you can have angular momentum without spinning right here, as we'll see right here. So now, let's look at a case. We used momentum for collisions, but let's talk about a rotational collision. Suppose we have a disk that's spinning in, let's say, one direction right here. And we have another disk that's spinning in the other direction, has a different mass and different radius. And we just kind of, from a very small height, we drop it onto there. Well, then what are they going to do? Eventually, they'll have the same, there might be a little bit of slipping going on there, but eventually they'll be moving together right here. And if we look at the torques, any torque that these guys exert on each other, the frictional, they're all going to cancel because we're looking at the entire system right here. So if we look at our angular momentum equation right here, I'm going to call everything going around this way positive, which means this way is positive. And we get the angular momentum of this one. Since this is going the other direction, we subtract off this one right here. And then after they stick together and they're moving together, it's just the sum of the two i's times omega. This was just like two objects coming at each other and colliding and sticking. What did we say? We said this momentum minus this momentum, and then when they stuck, and let's say they went off that way, you added their masses times their final velocity. It's exactly the same way. So we just divide out the i's right here, and we plug in what the two i's are. I1 is 1/2, that's a disk, m1 r1 squared. I2, 1/2 m2 r2 squared, and the same with the sum. Now I wanted to simplify the algebra here, so I said let's let m2 equal 2m1 and r2 equals 2r1. So that way I can at least simplify this down a little bit more. And I can cancel out the M1s and the R1s. And so then we just had this right here, which is omega 1 minus 8 omega 2 over 9. And just to even simplify it more, I said, let's let omega 1 be 10 omega 2. So this one's spinning 10 times faster than that one. So you got 10 minus 8, which is 2 ninths. So there's the final angular speed when they stick together right here. Now, if I wanted to figure out how much work due to friction, there would be some slipping in there. Well, the friction is the only one doing the work, and we know the total work is the change in kinetic. So the work due to friction is just the total work on this, which is just the change in kinetic. So here's the change. Here's the final kinetic, 1/2 I final, omega final squared, minus the initial kinetic. Well, there's two of them, so I have to subtract off both of them right here. Okay, so now all I have to do is plug in what the i's are, right there, plug in my i's using these simplifications right here, plug in my omega final right into here, and subtract right here. So if we got a little messy right there, but it's, you can follow the algebra and you just subtract. And so here, combining all that term and pulling out the m r1 omega 1 squared, there's the final kinetic minus the initial kinetic. And I just combine these two and combine these two. I just left it like that right here. And you'll notice that this term is bigger than that term. This is a negative number. Why? It's the work due to friction. Work due to friction is always negative right there. If I ask for the fractional energy loss, the fractional energy loss, how much you lost is the initial minus the final, and then you want a fractional, so you divide it by its initial. Well, I know that this is the final and this is the initial, and so I know these terms are going to cancel out of the numerator and denominator, so I really only have to take the initial, which is the 9/4 minus 1781 over 9/4. And I just plugged it in. It's about 90% of the energy I'm going to lose right there. Okay. Okay, so there's that one. Now, instead of dropping a disc on there, here I just have a merry-go-round or disc, and I just have a person out on the end, and he's just going to run into the middle. This thing is originally spinning. They're both spinning together, and then he just runs into the middle of the disc. Now, I for a person, he's just a point mass. Since I is defined as mr squared, and he's just 1 point, when he's out there on the rim, his I is just mr squared. Okay, so now we can write out the momentum equation. Here's the I of the disk and the person times his omega naught. And then when he runs into the middle, his I becomes 0 because his radius is 0. So it's just I of the disk right here. So we have omega prime is, solving for omega prime, divide this thing out. We get I of the disk, its mass is 5m times r squared, plus the person, mr squared, divided by the disk right here. The mr squares all drop out, you get this, and then this just simplifies, multiply top and bottom by 2, it's just 7/5. It's a little faster, it should be, he ran to the middle. It's like the ice skater pulling in her arm, she's going to spin faster. If we wanted to find out how much work it took for that person to run to the middle, well, he's the only one doing any work, so the work due to the person is the total work. That's just the change in kinetic. Change in kinetic, that's just the final kinetic energy minus the initial kinetic energy. It's all rotational right there. So we just plug in. The final I is 5/2. We already knew that right there. Because that was just this term right here. It was 5/2, just the disk. Omega final squared minus 1/2 I naught, which is the sum of the two, omega naught squared. So if we just subtract those two terms, I can factor out and get a common denominator here. This is 14/20 or 7/10 m r squared omega naught squared. Now, I could have said maybe when he first starts out, he's on the verge of slipping. If he's on the verge of slipping, he'll never make it in, but we could just say when he's out there on the end, his friction is what's keeping him from flying off, which is mv squared over r. And if he's on the verge of slipping, we can set the friction equal to mu Sn, which equals mu Smg. And so we could actually, if by equating these two, we could get the mu s right there. Okay, so there is, whenever you see someone running into the middle, you're probably thinking of angular momentum. If someone was standing on the side pushing you, you wouldn't use angular momentum because then you'd have to include the person, and the person is connected to the earth. You'd have to include everything. You'd probably use forces right here. Well, suppose over here, one last one right here, we have an object moving. This is a top view of a stick right here. It's pivoted so it can rotate about the center. So it's a stick that can just go around like this. And we're going to throw a piece of clay or something, some mass that sticks to it. When it hits it, it's going to make this spin right here. But it's not spinning at the beginning right here. So again, this is a top view, and there's no friction when this thing goes around. Now, again, we can look at torques about this point, because whenever force this guy puts on the little mass there, this one applies an equal and opposite force back, two normals. They both, when you look at the entire system, there are no torques about this point. There are forces on this point, but we're looking at torques about that point, so we don't care. Okay, so we can use angular momentum. Now, since this thing's coming in straight line, it does have angular momentum about that point right there. We can't use I omega. We have to go back to the general definition, which is r cross p. R is from here to here. P is mv. So it'd be L over 2 times mv. So that's where I get, there's the beginning angular momentum. It's L over 2 times mv naught. Then once it sticks and it's going in a circle, then we can use our I omega, because you're going in a circle now, and it's I of the stick plus I of the point mass times omega. Okay, and we know I of a stick about the center is 1/12 ml squared, and I for a point is mr squared, but r is just L over 2, so it's mr squared omega final. So then I just canceled an m, canceled an L, and so we're just left with V naught equals 1/12 L plus 1/4 omega final. I can combine these two, which is 1/3, and then bring the 3 over to the other side. So there is the omega final, how fast this thing will be spinning afterwards. If I wanted to figure out how much energy was lost in the collision, it's definitely losing because it's an inelastic, it's sticking together. So we could just say the energy before, now we can just say it's 1/2 mv naught squared, it's just going in a straight line, minus the total kinetic afterwards. It's all rotational, so it's 1/2, or remember these two combined together was 1/3 ml squared times my omega final squared. And so factor out the 1/2 mv naught squared, you get 1 minus 3/4, which is 1/4, and a 1/2 gives you 1/8 right there. So there's how much energy was lost. Or if I wanted to get the fractional energy loss, you divide it by what you had at the beginning, and the mv naught squares drop out. The 1/8 over 1/2 is 1/4, or you lost 25% of your energy when this thing hit right here. Okay, just remember when an object's going in a straight line, it can have angular momentum at that point. It has no angular momentum about this point, but it does have angular momentum about that point. Why? Because it was able to give this object a spin right here. Okay, and if you're spinning on an axis, use the I omega. If you're not, use r cross p. Okay, so there's angular momentum.